Hello everyone. In this video, we'll complete solving exercises on Silo theorems and rings. We will start with the first exercise. Let R be a commutative ring with 1. If A be in R such that A is unit, so invertible, and B power 2 is equal to 0, show that A plus B is invertible. Solution. We compute A power minus 2 A minus B dot A plus B equal A minus 2 into A power 2 minus B power 2. A minus B into A plus B is equal to A power 2 minus B power 2, since R is a commutative ring. Okay, so now expand A minus 2 A2 is equal to B power 2 is equal to 0. So this left us with A minus 2 dot A power 2. A minus 2 dot A power 2 is equal to A inverse dot A power 2, which is equal to 1 power 2, which is equal to 1. And this establishes that the inverse of A plus B exists and is equal to what? Equal to A inverse power 2 by multiplied with A minus B. This is the first exercise. The second exercise, he is asking about Z6. Is Z6 a subring of Z12? The answer is definitely no. And we will mention the reason. If we have R, a ring, and S subset of R, we say that S, here is clear that Z6 is a subset of Z12, but S subset of R is a subring of R if and only if S, A minus B belongs to S, whenever A and B belong to S, and A dot B belongs to S whenever A and B in S. So Z6 alone is a ring, Z12 alone is a ring, but we cannot see or we cannot view Z6 as a subring of Z12. The operations done in Z6 modulo is modulo 6. The operations done in Z12 is modulo 12. So in Z6 we have 4 plus 4 is congruent to 2 modulo 6. But 4 plus 4 is congruent to 8 modulo 6 in Z12. So these are two different elements, and we cannot see or we cannot view, as we mentioned, Z6 as a subring of Z12. We have two different operations. Now, exercise 3. Determine the class equation for non-abelian groups of order 39 and 55. We will start with the groups. So solution, we will start with the groups of order 39, that G is non-abelian and the order of G is equal to 39. Which is 3 times 13. Now, the class equation is order of G is equal to order of the center subgroup plus summation over the indices of the centralizers, of the non-trivial centralizers of elements in G. So let's find first the order of ZG. We know that ZG is a subgroup of G's. The order of ZG must divide the order of G. So the order of ZG is 1, 3, 13, or 39. Okay, so if order of Zg is equal to 39, then Zg is equal to the whole group G, and so G is abelian, which contradicts our assumption that G is not abelian. So if order of Zg is equal to 39, then G is equal to Zg, and G is abelian, a contradiction. Okay, if the order of Zg is equal to 13, we know that Zg is normal in G, so we can quotient G by Zg, and the factor group G by Zg has as an order 39 over 13, which is equal to 3. Then G over Zg is cyclic. When G over Zg is cyclic, then G is abelian, a contradiction again. Similarly, if the order of Zg is equal to 3, we find a contradiction again, and we find that G is abelian. Okay, so this left us with 1. The order of Zg finally is equal to 1. 39 gives a contradiction, 13 gives a contradiction, 3 leads to a contradiction also, and so the order of the center subgroup Zg is equal to 1. Now we need to find this summation. And 13 is the number of Silo 13 subgroups of G, is congruent, as we know, from Silo theorem to 1 modulo 13, and 13 must divide 3, and so and 13 is definitely equal to 1. No other choice. So there is one and only one 13 Silo 13 subgroup of G. We will call it H1. Okay, so H1 is the unique Silo 13 subgroup of G. Okay, there are 12 elements, 12 non-trivial elements in H1, each of order 13, yes, and these elements by conjugation still in H1, since H1 is normal in the group G. The conjugacy classes, we know that the order of each element, the order of the conjugacy class of each element is equal to the index of G, index of its centralizer in G. Okay, so this is equal to 3, so the size is 39 over 13, which is equal to 3 exactly. So the order of these conjugacy classes for elements in H1 is equal to the size is equal to 3, as you see. The size is equal to 3, and they must partition 12. Okay, so 12 can be partitioned using 3 in just one way, which is 12 can be written as 3 plus 3 plus 3 plus 3 4 times. Now this left us with 26 elements, with 26 non-trivial elements, each of order 3. Each of order 3. Okay, so the size of each conjugacy class of these elements is equal to 13. So we need to partition 26 using 13s. Okay, this can be good. This can be done in one way, which is 26 equal 13 plus 13. Finally, the class equation of our group is given as 39 is equal to 1 plus 3 plus 3 plus 3 plus 3 4 times plus 13 two times. Okay, so this is the class equation of a non-abelian group of order 39. Same argument. We will proceed for groups, for non-abelian groups of order 55. So now suppose that, or assume that the order of our group is equal to 55, and of course G is non-abelian. 55 can be written, prime factorization is 5 times 11. Now again, we will find the order of the center subgroup. Order of the G must divide the order of G, so order of the G belongs to 1, 5, 11, 55. If the order of ZG is equal to 55, then ZG is equal to the whole group, which implies that G is abelian, so this case is not allowed. If order of ZG is equal to 11, then the factor group, then the order of the factor group G by ZG is equal to 5. This means that G over ZG is cyclic, and so G is abelian, a contradiction. A contradiction. If order of ZG is equal to 5, if order of ZG is equal to 5, then the order of the factor group G over ZG is equal to 11, and G over ZG is cyclic, which implies that G is abelian, a contradiction. So we have only one possibility, which is 1. The order of the center subgroup is equal to 1. Now N11 is the number of CeLO 11 subgroups, and M5 is equal to the number of CeLO 5 subgroups. N11 is congruent, as we know, to 1 mod 11, and N11 divides 5, so N11 is equal to 1. And there is one and only one CeLO 11 subgroup of G, which we will call it, which we'll call H1. Okay, so H1 is the unique CeLO 11 subgroup of G. Now M5 is congruent to 1 modulo 5, and M5 divides 11. So M5 is equal to 1 or 11. If M5 is equal to 1, then we can write G is isomorphic to H1 times H2, where H1 and H2 are two abelian groups, implying that G is abelian group, which is a contradiction. Okay, so as the argument in the case where the order of G is equal to 39, same argument. This implies that the order of M5 is equal to 11. So n of 11 is equal to 1 and n of 5 is equal to 11. We have one and only one CeLO 11 subgroup of G and 11 CeLO 5 subgroups of G. The size of the conjugacy classes of the 10 non-trivial elements in H1 is equal to 11, is equal to 5, sorry, is equal to 5. And they must partition uh, 10. So this could be done in one way. So 10 is equal to 5 plus 5. We conclude that there is two distinct conjugacy classes for the elements of the subgroup H1, the CeLO 11 subgroup of G, each of size 5. This left us with 11 elements, 44 elements, 44 elements of order 5. The conjugacy class of each element of these elements is of size 11. Okay, and they all the orders partition 44. So to partition 44 using 11s only, this can be done in one way. 44 is equal to 11 plus 11 plus 11 plus 11 4 times. We conclude that the class equation of G is as follows: 1 plus 5 plus 5 plus 11 plus 11 4 times. Okay, plus 11 plus 11 plus 11 plus 11. This is the class equation of non-abelian groups of order 55. Okay, so now we'll turn to the last exercise in this set of exercises. Exercise 4. Consider a group G of finite with finite order which is 200. 200 can be written as 2 power 3 times 5 power 2. This is the prime factorization of 200. So that G is not simple. G is not simple. We need to find a non-trivial normal subgroup of a G. Okay, so we need first thing we could think about is to find unique CeLO subgroup of G, and we are done. Once we finish the proof, we conclude that any subgroup of order 200 is not simple. Is not simple. And 5 is the number of CeLO 5 subgroups of G, and 5 must be congruent to 1 modulo 5, and 5 divides 8. So M5 divides 8 is equivalent to say that M5 belongs to 1, 2, 4, 8. Which of these elements is congruent to 1 modulo 5? The only possibility is 1. Okay. So this is a simple exercise, and 5 is equal to 1, and so there exists a unique below 5 subgroup of G, which is therefore normal. Name it H, is normal in G, and H is a non-trivial subgroup. The order of H is equal to 5 power 2, which is 25. Order of H is equal to 5 power 2, which is 25. H is a non-trivial subgroup and normal in G, then G is not simple. Next we will start with polynomial rings, chapter 9, part 1.